Okay, 19.3, sulfonation. So we're going to go through the same process as we did before with EAS. Is we're first going to prepare an electrophile, and then we're going to go through, as I said, the same process. So now the electrophile in this case is SO3, sulfur trioxide. We prepare that, we make that by getting something called fuming sulfuric acid. No idea what that is, by the way. My guess is it's just really concentrated sulfuric acid, and some way we get SO3 in there. All right. So fuming sulfuric acid. Here, my coffee's getting made in the background. Hope that's not too distracting. Fuming sulfuric acid consists of sulfuric acid and SO3 gas. So in this bubbly mix, which you don't want to drink, is a bunch of SO3. I'm just circling stuff today, aren't I? Is a bunch of this sulfur trioxide. Now we're going to explain how this is electrophilic, but look at this electron density map. So if you were to make sulfur trioxide with a computational chemistry program like Gaussian, you could make an electron density map, and that shows you the red spots are the hot spots where there's lots of electrons, and the not red spots are where there's not enough electrons. And so can you see that you have a sulfur atom here in the middle and a bunch of oxygen atoms? That's a sulfur, and here's an oxygen atom, which just looks like a circle, I guess, when I draw it like that, right? But oxygen atom, okay. So why are the electrons out here so much? And also, you can't tell by looking at this, but this is trigonoplanar. Which makes that sulfur atom an excellent target. Wow. Makes it a very good electrophile, right? Excellent target. It's electron poor, and it's flat. It's easy to get to. It's electron poor, and it's flat. Wow. All right, so let's look at the mechanism now. Now that we've considered preparing the electrophile, we now have, which I'm going to use in class, our electrophile. That's our electrophile right there. Whoops. That's our electrophile right there. Okay? All right. So, looking at sulfur trioxide in more detail. Say it out loud, please. Sulfur trioxide. And I'm not teasing when I say that. I hope you don't feel silly doing it, but say it. Sulfur trioxide, SO3. The SO double bond involves a p orbital overlap, no big deal, but it's less effective than the orbital overlap of a carbon-carbon double bond. Why? So look at this carbon-carbon double bond here. This is a single bond, and here's our pi bond, which is above and below the plane, right? Side-to-side overlap makes a pi bond. And here's our sigma bond right in the middle. End-to-end overlap. Now, when you have lots of overlap between those two orbitals, you get a molecular orbital, which is quite efficient, right? It's drawn two different ways here so you can see it. But with the sulfur oxygen pi bond, it's not very efficient, all right, because of the shapes here. Do you see that? You're not going to get as good of overlap, and also because of the bond length. So the shape and the bond length make it so you don't get very good overlap. But when you don't get very good overlap, then it turns out that this becomes, the pi bond is weaker, and the SO is considered more of a single bond, right? And I'm going to go back a slide for a second, okay? So that's why the electrons, that's why this is so electron poor, was because the pi bond this is really more like a single bond than a double bond. Okay? Now, what does that tell us about the charges? If the electrons, I'm going to go back on the slide again, what would you say about the charges in this oxygen here? Well, you'd say it's definitely partial negative, right? Can you see that? And that's definitely partial negative because of all that red. Look at that. Okay? So what does that tell us about the sulfur? Right? The sulfur then is going to be partially positive. So what I've got here is a partial negative, partial negative, a partial negative, and really a bigger partial positive here, right? And it's flat and it's big. So this makes this an excellent electrophile. Right? So the first thing, just like in halogenation, the first thing we did was make a good electrophile. So this makes this an excellent electrophile. These pi electrons then, just like last time, come in, attack that electrophile. Did I say that right? These electrons acting as a nucleophile, right? That's the nucleophile here. Come in and attack that sulfur as the electrophile. And then when the ring attacks the sulfur trioxide, the carbocation is resonance stabilized. So you can see that here. This picture here, by the way, is shared between the next couple slides, so watch out. This is a little bit clumsy, I think, presentation of this, but if this goes here, this is resonance, okay? So make sure you have a resonance arrow, big deal, resonance arrow. Draw the structure here. Pause the video and draw the structure here. It's on the next slide, but you should practice this. Okay, did you draw it? I hope you did. If you did, you're getting some value out of these exercises, okay? So it looks like that's going to be a hydrogen here. This is going to be an SO3 minus. Okay. Now these electrons go over here, so that's going to be here, and these are still here, right? And that's what we have. This is the result of that. So hopefully you drew that. All right, let's go to the next slide. You're going to see this picture. This is on the next slide because it's this carbocation stabilization is continued on the next slide. All right, so there it is right there. Okay, you see it? Now this one is, right, so if these electrons come here, then I've got my new double bond here, right? That's what that's about, okay? But from the previous slide, I'm going to redraw that. Right? Right? And that's going to resonate. So you've got 3 resonance contributors here. Okay? And that is the sigma complex. All right, I feel like I hear something burning. Yes, I do. Water's boiling. Smoke, please. I'm in the kitchen and I heard something boiling. It was just water, but... All right, so that's the sigma complex. And this is the resonance stabilization. So I'm going to tell you, draw the resonance hybrid. Draw it now. If you don't know how to draw it, then go back to lesson 19 or video 19.2 and see how I drew that resonance hybrid. If that's not good enough, then bring it to class to me. Very important that you can do this. It's going to give you lots of power. All right, now that we have that, this is done in aqueous solution. Right, so these electrons are going to come in and deprotonate. This always happens in every EAS, every one. We get a deprotonization so that we can restore aromaticity. Okay, after we restore aromaticity, boom, we're done. We're basically done. Okay, so Klein is showing, one last step here where you get rid of the formal charges. He's just doing this to clean this up, but this is very much an equilibrium. It's actually a pretty strong acid, so probably it's just as much. It just as much goes toward the hydronium ion as it does the water. All right. So the spontaneity of the sulfonation depends on the concentration. So this can go both ways, and you need to memorize both of these. So this goes this way, And then if you dilute, it goes the other way. You can take it off. Okay? We'll look at this more in more detail later. For now, go back and do conceptual checkpoints 19.2 and 19.3.